Good afternoon. I'm Caleb Pollack, your host for today's webinar. On behalf of the AAPG Petroleum Structure and Geomechanics Division, I am pleased to introduce our speaker, Qiqi Wang. Qiqi is a Ph.D. candidate in Geological Sciences at UT Austin, working with the Fracture Research and Application Consortium at the Bureau of Economic Geology. While at UT, she's had opportunities to look at natural fractures in various locations of many different ages and within different rock types. Two of Qiqi's primary dissertation tasks are to integrate outcrop and subsurface data to gain a better understanding of how deformation and diagenesis together influence reservoir properties, adopting and adapting various statistical methods to improve diagnosis and prediction of fracture attributes and patterns and rock properties. Concurrently with her Ph.D., Qiqi is pursuing a master's in statistics at UT and is learning to apply those skills and techniques to the analysis of petrographic and fracture data. In addition to her work, Qiqi is an animal lover, as you can tell by the screensaver behind her, and an avid cook, as well as an outdoor enthusiast. Today's presentation is being recorded and will be posted on the division's YouTube channel in a few days. For any questions you have during the presentation, please use the Q&A button at the bottom of your Zoom screen, and we will address those in the order in which they come in. With that, I'll cede the floor to Qiqi.
Thank you very much, Caleb. And I'm going to share my screen now. Oh, sorry. 12 o'clock. That was my cat feeder, if you can hear it. Let me share my screen. Yeah, can you see my screen? No, maybe not. Can you see it?
Yep, we're good.
Okay. Awesome. So good noon, you all. Thanks for the introduction, Caleb, and thanks a lot for having me here at the webinar today. So I'm Qiqi. I'm a PhD candidate from the UT Austin, and I'm also a graduate research assistant at the Bureau of Economic Geology. And well, I know most of you are probably looking at the right-hand side image. You can see my mouse. I'm trying to bring up the laser pointer. So this figure here, I know it's fascinating. It's actually one of the photomicrographs that got me interested in studying fractures and reservoir quality in tight sandstones. So this figure here is revealing the internal structure of an open natural fracture in tight sandstone in the Piceance Basin. So in this figure, you can see the darker outside zones are the reservoir rock hosting the fracture, and you can see the fracture walls, and you can also see the pillars of cement mineral grow into the fracture open space. So observation like this can help us to better understand how deformation and diagenesis together modify the reservoir property. Just a little bit more about me, I guess. At UT, I got opportunities to expand my horizon by looking at natural fractures in various locations, ages, and rock types, both conventional and unconventional. And on this map, I'm highlighting the places I've worked and the ages of rocks. And I study subsurface data and outcrops. Field work is most of the time a team effort, and I'm really grateful for all the support from my advisors, Steve Laubach and Julia Gale. And huge thanks to my incredible field squad. Concurrently with my PhD, I'm pursuing a master in statistics. And apart from my work, I'm an animal lover. Here's my cat, furry friend Tommy, and I love to cook and all the outdoor activities. So with that, before I get into my sandstone study, I would like to take a minute sharing my work characterizing spatial distribution of joint in an Archean basement outcrop in the Grand Teton. So why are we interested in fracture clusters in this basement outcrop? So our study outcrop may be an analog for fracture zones in subsurface granites, where the effect of fractures on fluid flow and rock strength are issues. So with that motivation, we set up scanline to capture 1D fracture intensity across a 200-meter granite exposure. And at this large granite pavement, we can see areas with closely spaced, long, thin joints adjacent to areas with no joint. And here I'm showing some water flow from a joint in a gneiss that at the nearby Snowdrift Lake. Actually, many of these joints in a Teton are fluid flow conduits present day. So when we compare this outcrop with, for example, the Lancaster Reservoir off Shetland, which is producing oils from fractured granite, gneiss, and some other higher grade metamorphic rocks, the basement rock type here in the Teton closely resemble that at the Lancaster. Plus, the size and shape of the off Shetland is comparable to that of the Teton Range. At the off Shetland, the fracture zones are around 15 to 75 meters wide. That is comparable to the fracture zone, or what we call fracture cluster width in our outcrop here in the Teton. Hence, we say this outcrop study is notable for providing insights based on a clear and a readily accessible view of point clustering in basement that may not be identifiable with seismic. And this work was published in the Petroleum and Geoscience Journal. And I do want to emphasize that in this study, I applied a quantitative method or a software developed here at UT to analyze fracture distribution. So really the advantage of what we call the NCC method used here is that we can generate objective, reproducible, statistically defined fracture cluster widths and spacing values of the basement outcrop analog. And later in the talk, I will show you an example where we use this method to analyze a subsurface fracture data. And now, as promised, let's get into understanding fractures and reservoir quality in tight sandstones. But why we care? Here, I want to tell you about the frontier blowout to demonstrate the importance of understanding natural fractures as they impact reservoir properties, and they might also lead to drilling and operational hazards. So this incident happens on the Madden anticline. It's a 20 miles long and 10 miles wide anticline laying in the deepest part of the Wind River Basin. It is a classic overpressured deep basin feature, and this Madden field is a natural gas field drilled and developed on this anticline. The natural fractures has allowed the pressure developed to move up to shallower, more permeable and porous sandstones, and the resulting recoveries has been impressive in the Madden anticline. However, the fractures behaved well until they did not, right? So in April 1992, the Bighorn 336 well, that's this well right here, it blew out when penetrating the frontier formation before landing the underlying target, the Medicine limestone. So this well started blowing out sweet gas for an hour before igniting itself. And there are no unique reservoir property related directly to deposition of the formations of the Madden field. What does set Madden apart is the presence of intense natural fracturing and geopressuring. So here in this plot, we can see frontier sandstone is overpressured. Similar situation in the shallower Mesa Verde sandstone, which is also another tight reservoir. And the natural fractures in the Madden field have led to many unpredictable, often dangerous incidents for over 2 decades. If you can think of other reservoir whose property or behavior is strongly impacted by natural fracture systems, please just feel free to put them in the chat if you like, and we can have a discussion in the end. So with that, here I propose 2 major discussion topics for today. The first one is mechanism for open fractures at reservoir depth in a sandstone with long diagenetic history. The second one is what are the primary controls on fracture abundance and spatial distribution within the East Painter Sandstone Reservoir? And here I want to give you a little spoiler on the key messages. So the first one is a residual fracture porosity preserved at great depths for tens of millions of years under diagenetic conditions. And we discovered the rock composition matters, and Feldspar and lithics can help retain fracture porosity under extensive quartz cementation. And also the structural position matters. The fracture pattern and the character varies with structural position. And after my talk, hopefully we can gain some alignment, understanding the importance of natural fractures in tight reservoirs. And also hopefully I can provide some technical guidance to tight sandstone reservoir characterization. Just an outline of what I'll cover. I'll start with small scale. I'll show example that cement morphology and porosity preservation within fracture varies, and explain how these cement help keep fractures open and for how long. And I will briefly introduce how we use fracture cementation to infer timing of deformation. Then I will move on to a reservoir scale fracture characterization, introducing the key findings from a case study in the East Painter Reservoir sandstone. All right, now you might want to see what a partly filled natural fracture look like in the subsurface, right? So here are 3 typical cement morphologies that sometimes can all be seen within a single fracture as we move from the tip to the center. So towards the tips and in the smallest part of the fracture, typically we see sealed textures where the fracture zone is nearly completely filled by quartz cement. That would be the case A. While near the center of the larger fractures, at its widest part, we often see the fracture wall is just lined with euhedral quartz overgrowth, but the bulk of the fracture is either the porosity or might be filled by some later stage cement, such as calcite. That would be the case C. And in the intermediate position, the case B, we see a lot of pore space within the fracture, and we commonly see what we call bridge structures, where a pillar of quartz cement bridges across the fracture, across the natural fracture, spans from one wall to the other. And these cement bridges we see here, they contain valuable information about fracture timing, and they can reveal history of diagenesis and deformation of the rock. It's really pretty cool, and we will get into that later. Here, I'm just showing fracture cement in natural fracture in various rock types. So they do not just exist in sandstone. From left to right, we see cement bridges and open pore space in the fractured stone. And this second picture, we are looking at the fracture phase of a piece of core of the New Albany shale. We see the cement bridges are actually patches of minerals growing on the fracture surface with spaces in between. Those would be open pore space in the cross-sectional view. And we see patches of, right here in the left one, similar feature found in the Mesa Verde sandstone core example. We see patches of quartz growing on the fracture surface with space in between. So now we've trained our eyes seeing internal of a natural fracture and then how it looks. This slide here presents a study by Lander and Laubach. So they listed several factors affect cement precipitation in fractures. So those factors can help infer under certain thermal conditions whether we expect to see just a thin layer of cement lining the fracture, or cement can grow as bridges but still remain a lot of pore space, or maybe we'll end up seeing a fully filled fracture, which would not be conductive. Let's start with the first factor, the temperature. It governs the quartz growth rate. The higher temperature, the faster growth rate, right? Faster quartz cementation growth rate. And the second factor, whether the cement crystal reaches euhedral state or not, is important, because we know cement nucleation becomes much slower after achieving a euhedral state. If you allow me to play this animation right here in this corner, and if you look at this animation, it's showing the opening and sealing in the fracture. You can see the rock composition matters, since quartz tend to grow on quartz, so the lighter color grains are the quartz. We see these pore space associated with non-quartz grains in the rock. Actually, according to Lander and Laubach, the grain size and the crystallographic orientation also matters, but we do not discuss them in this talk. So back to this simulation, it reveals there's a competition between fracture opening and quartz cementation. We can play this again. Yeah. Yes. And whether the fracture can be sealed or not also depends on its opening, the fracture opening rate. So if a fracture opens fast with large enough displacement, the cement growth cannot keep up with the fracture opening, then we will end up with a lot of pore space within the fracture. Well, so all these seems to make a theoretical sense, but do we see proof of the theory in naturally fractured sandstones. Now let's look at some real rocks. Here is a map showing the studied Cretaceous frontier formation sandstone outcrop at well locations. So lithology is consistent throughout the study area. The samples have the same composition, litheranites to sublitheranites, and the grain size is comparable among the 3 locations. Well, I picked the same fracture set across the basin. Now, the only difference between the outcrop, the intermediate, and the deep core scenario is that they are at different present day depths. That is to say, we sampled over a wide range of thermal histories to investigate quartz cementation within natural fractures. Now, let's compare how the cement looks within those fractures over a wide range of thermal histories. Let's go through the 3 scenarios one by one from left to right. So the left is the outcrop scenario. The rocks in the outcrop are buried to maximum 2 kilometers depth. And here we're looking at an open fracture surface. We see negligible amount of quartz cement lining the fracture surface, indicates that the fractures are generated in the subsurface. Then they got brought up to the surface and split open in the outcrop. While we see in the figure B and figure C are core observations. So they further show that the amount of quartz accumulation depends broadly on thermal exposure. If we compare the intermediate burial and the deep burial case, we see more extensive quartz deposits in the hottest, the mostly deeply buried fractures. And I want to emphasize that even in the most deeply buried, hottest examples, we still got cement bridges texture, and we still see a lot of open pore space. Now, I would like you to pay attention to some features in this rightmost image. This is a representative internal texture of a natural fracture with quartz cement, actually from the same core, from exactly this core right here. And this image is from a 6.2 kilometer depth, so pretty deep. And what we see here is we see transgranular microfracture cutting through multiple grains, including a few quartz grains and also some feldspars. And do you see where are the pores? The pores are the green ones. So the pores, the pockets of porosity occur where the fracture cut through a non-quartz grain. So the non-quartz grains are unsuitable substrates for quartz overgrowth nucleation. So in other words, the quartz cement likes to nucleate on the fresh surface of a cracked quartz grain, but not on the surface of a feldspar grain. And I also want you to pay attention to the quartz cement crystal grow into the pore space near the feldspar, those ones. So you see the faceted crystal faces. So they mean the quartz crystals reach their hydral state. They had enough time and they have enough space to grow, but the cement just never enough to fill out the pore space associated with the feldspars. So this is another strong evidence saying that the feldspars, and in some cases we can have lithics in the rock, they help retain the fracture porosity. So with that, another question arises. So when were the fractures formed? And the fractures have been open, but for how long? And answers to such question can have implication applicable to studying from deformation and diagenetic history of the reservoir. You can study fluid migration, etc. So what's fascinating is that the fracture timing information can be revealed by those tiny fluid inclusions trapped within the cement mineral during repetitive fracture opening and sealing. So in this picture, you can see individual inclusions forming trails of inclusion trapped in the crack, and we call the trails of inclusion a fluid inclusion assemblage. The fluid inclusion assemblages can tell us the temperature, the composition, and the pressure of the fluid, the fluid flowing through the fracture when it was forming. Then we can put those trails of inclusion in relative time sequence based on the cement texture. For example, on this image right here, the zone 1, 2, 3, 4, and I also have a 5 here are sorted by age. So with 1 being the oldest, and we have the 4 and 5 being the youngest. And if you pay attention to the width of the zones, they're different, right? So the later formed trails, the zone 4 and the 5, tend to be wider and they cut through some early cement. So by doing this type of mapping, for instance, we see temperatures recorded in zone 1 is lower than in zone 2, and the temperature recorded in zone 2 lower than zone 3, and in zone 4, if we say the temperature recorded is higher than 1, 2, 3, then we know when fracture was forming, it was buried deeper, while the time of zone 1, 2, and 3, but got uplifted during forming of zone 4 and 5. So if we map that time and temperature sequence to the burial history curve of our intermediate core, with measured in situ fluid temperature being around 142.5 to 165.5 degrees C, then we can locate when our fracture was formed in the burial history. So in our intermediate core example here, I show the studied fracture was active around 45 million years ago and stayed active for around a few million years. Then after that, it retains open pore space within fracture for around another 38 million years. Obviously, there's uncertainty associated with this type of analysis I want to emphasize, and it really requires a good basin model and really good fluid inclusion measurements to make this method to be valid. And what is interesting is that these fractures I studied are striking east-west. They are perpendicular to the current maximum horizontal stress. So normally we would expect fractures of such orientation to be closed due to the maximum horizontal stress orientation, but they remain open. We would like to know why. Our hypothesis is the cement bridges we study. Right, I'm showing examples here. The cement bridges goes from one fracture wall to the other, and they can hold the fracture open under unfavorable stress condition. So with that, we believe with the just right amount of cement, the fracture cements can help maintain stress-dependent conductivity during reservoir depletion. Also, I want to mention the extensive cement in the rock mass, in the host rock, will make the matrix rock stiffer, and that will help retain the fracture open as well. And so the first part, the key findings. Yes, before I get into this reservoir scale fracture characterization, the key finding of the first part of my talk, we see residual fracture porosity observed at great depths, deeper than 6 kilometers, above around 165 degrees C under diagenetic conditions. We see residual fracture porosity, and the porosity persisted for tens of millions of years under diagenetic conditions. Feldspar and lithics can help retain fracture pore space, and cement bridges may help maintain stress-dependent conductivity. So that's that. And now let's switch gears. Let's moving on to the reservoir scale subsurface natural fractures characterization. So this is subsurface study, and the abundance of fractures and their spatial arrangement impact fluid flow and the rock strength in the subsurface that we know, but are very challenging to measure in the subsurface. With the coring procedures available, the open fractures are largely undersampled in the subsurface. Hence, the pattern of natural fractures are usually not well understood and really hard to predict away from the wellbore. So in the Nugget formation, the reservoir is producible actually conventionally with horizontal wells, but the fractures are thought to add to the reservoir permeability and can result in high flow rates. On the other hand, if fractures are closed and impermeable, the reservoir compartmentalization could exist. Besides, at East Painter Reservoir, the fractures were identified as possible zones of lost circulation and rapid breakthrough of water or natural gas, which are undesirable. So with that said, I would say the data for this project includes image logs sampled continuously along 13 horizontal wells transects Nugget formation in the East Painter Reservoir. And the objective includes characterize fracture spatial arrangement patterns in a strongly folded, structurally simple oil field anticline. And we want to test the correlation between fracture character, their attribute, intensity, and the structural position. Here, I want to show the structural cross-section through the Painter and Painter Reservoir structures. You can see faults and fault geometries. You can see the projected well trajectories and stratigraphic units. The studied horizontal wells here are all drilled to drain the oil layer, and the East Painter Reservoir anticline is right here is asymmetric with a steeper forelimb and a gentler backlimb. In terms of rock type, the Nugget Formation consists of massive, competent, fine to medium aeolian quaternite with quartz cement. In terms of fracture abundance, our first key finding is the overall fracture intensity in forelimb of the fold are 2 to 4 times higher than that in the backlimb. However, we want to be careful because the hinge and the forelimb, although the fracture intensity is high, many of the fractures are sealed. For example, the well on the left example, the fractures on both the hinge and the backlimb of the anticline here, I'm showing the fracture intensity. And please see the intensity of open fractures versus all the fractures, right? We see, so the hinge section of the swells show higher overall fracture intensity, but fewer open fractures. It tells us a large proportion of the fracture in the hinge interval of the swells are sealed. On the other hand, most fractures in the backlimb are open. And similar in this well on the right side, which was drilled into the backlimb and penetrate through the hinge and the forelimb. In this well, we see most of the forelimb fractures are sealed. In contrast, those at the hinge zone at the backlimb are open. What if I'm not satisfied by just looking at the intensity at locations? What if I want to generate more nuance about fracture patterns, such as are these fractures regularly spaced or are they more in a clustered manner? What about how wide is our fracture zone, fracture corridors, or what about the distance between fracture corridors or fracture zones? So such questions are usually answered in a qualitative, a more subjective way, but the normalized correlation count method we're using here can generate a statistically defined values of cluster widths and spacing. It also allows us to compare fracture pattern in different wells, so allow a fair side-by-side comparison between wells. And I want to start with this one. The blue line is the normalized correlation count curve, or the NCC curve generated from the fracture data in our studied horizontal well. So the key thing here is wherever the blue line is outside of this gray envelope, we're seeing a signal telling us our fracture pattern is not random. So here our fracture are shown to be clustered. And we can also read principal cluster widths to be around 400 feet width, and an alternative cluster width can be read as 1,000 feet. And then we can read a principal cluster spacing of around 900 feet. So these numbers might be used for optimizing subsurface DFN models and can be used to guide engineering operations. And you may also apply this method to horizontal well data sets in your unconventional assets or for studying fault damage zone widths. So a wide range of applications. Also, if you look at the right-hand side, the two plots, the higher elevation and the steep slope of this plateau of the blue line indicates a higher degree of clustering in the analyzed data set. So the key finding here is that the gently dipping backlimb of our asymmetric anticline is showing a higher degree of fracture clustering revealed by the steeper slope of the blue line. And this is in general the truth among all the studied wells. And we also found despite the higher fracture density, the fractures at the forelimb are the least clustered. Okay, another point is here at the backlimb, the reoccurring up and downs in the box highlighted here. So these up and down the blue curve indicates we see regularly spaced fracture clusters. Now, we see the fracture abundance and pattern varies with structural position on the anticline. Now the question is, will these be something you want to consider in your well planning or well design? Well, if you are not convinced yet, it's fine. What I want to say here is in tight rocks, natural fractures do commonly occur, and they can be hazard, and they can be beneficial for production as well. And they are good to be considered if you're thinking about adjusting your reservoir models and well plans. And we can gain more proof from looking at the production. So I look at the cumulative barrel of oil equivalent, cumulative BOE, the production lifespan, and the total water production in each studied well. On the map, I have good producer in green and bad producer in red. So we see a definitive production difference between wells in the same anticline. We have 60% of the production coming from the top 20% producers, where the cumulative BOE of good producers can be up to 5 times of that in a bad producer. Here, the key finding is really that our best producers are mostly located in the gently dipping backlimb of the anticline, where natural fractures are mostly open and more clustered. Another interesting thing is if we compare that well, the well 12A and the well 14A, they're the 2 top producers, and they are both landing on the backlimb of the anticline. However, only very few fractures are recorded in the well 14A. Is this showing us we only need very few highly productive fractures to achieve high production? I would put a question mark right there, and I would love to hear your comment if you have seen other wells and reservoirs with similar behavior. Okay, so with the 2 examples, we can now have a discussion on one. I think this method called NCC or normalized correlation count method is useful. The abundance of fractures and their spatial arrangement are very challenging to measure in the subsurface. For assessing fracture networks, 1D observations are frequently all that we can obtain from the subsurface, from core or from image logs. And this NCC 1D can generate nuance about fracture clustering, including degree of clustering, the width, and the spacing. And we can get statistically defined fracture cluster width, or like if we're studying fault damage zone width, right? And the numbers generated are producible values of those width and spacing. So such info can influence your DFN model or your kinetics modeling. For example, the kinetics can only model a 1 mile times 2 miles area with a maximum 100,000 fractures. Thus, in many cases, you may need to simplify your DFN model before feeding it to the kinetic simulation. And once we quantify the principal cluster spacing and the width of the natural fractures from horizontal wellbore, maybe we want to make sure we maintain the trend in our DFN as we simplify it. And in the flow simulation, I would imagine with same number of total fracture, your DPDK model or your single porosity model would be very different. So for example, if your clusters are if your fracture pattern are super clustered, maybe you can treat your fracture cluster as one bigger fracture instead of many smaller fractures. And also this method is rock type and scale independent. So it can be applied to your tight sandstones, your shale reservoirs, your carbonates. So with that said, the key finding of the second part of my presentation, fracture abundance, pattern, and character can vary with structural position. We identified in terms of intensity, we see the steeply dipping forelimb has the highest fracture intensity compared to the hinge and the gently dipping backlimb. And we see the forelimb and hinge zones sometimes lacking open fractures, while most fractures on the backlimb are open. And also, despite high fracture abundance, fracture in the forelimb are the least clustered, and the backlimb can have regularly spaced fracture clusters. And also, this normalized correlation count method allows statistically defined fracture cluster identified in the subsurface data set. And my future work, I propose, I listed them here. Maybe we want to future investigate the size and the role of individual fractures, so we can have some production data while drilling. And intensity is not all, because we want to know if the fractures will be conductive or not. And also the investigate correlation between fracture clustering and the cementation. Do we see more clustering or less clustering with more cementation or less cementation? So there's a discussion around that, we see example of both. That might be worth future investigation and will allow us more predictive power. Okay, so after that, last but not least, I just want to highlight the implications of my work applicable to some future workflows in tight reservoirs regarding fracture characterization and reservoir quality. So it is possible to incorporate fracture study into reservoir quality characterization and prediction workflow when dealing with a naturally fractured reservoir. And honestly, I think we should incorporate fracture study into RQ workflow. And the second one is the core count software and the associated statistical method can be used to quantify not only the fracture pattern, but also the width of the fault zones if you're studying the faulted system. And such results generated are objective and reproducible. The last one, I would point out the fluid inclusion in fracture cement could be used to investigate hydrocarbon charge history, and you can use them as calibration points in basin modeling and temperature history predictions. Okay, so that's the end of my presentation. And here I would like to thank the Fracture Consortium and my sponsors and my committee member, and I would like to thank my co-authors. I know Vincent is in the audience. Vincent is probably not in the audience, but Wayne is in the audience. So Wayne and Vincent both helped me with acquiring that subsurface data set, the Nugget sandstone data set. And thanks for my field squad and Professor Julia Lamarche and Bertrand from Total for hosting France while we do a France a field trip. Okay, so I think that's that. And I'm open to questions.
Well, Qiqi, it looks like we have one question in the queue, and to anybody in the audience, if you have questions, please use the Q&A option at the bottom of the Zoom screen. So I'll go ahead and read it aloud just so we have it recorded. From Brown Hawkins, do you have any examples of calcite bridges in limestone reservoirs?
A quick question, a quick answer would be yes. We do have, I've seen calcite bridges in dolostone and in limestones. And I believe one of the citation, a reference paper I can recommend you to read is from Julia Gale. I can send it to you. It's about Knox dolostone that I show as an example here. So here is an example of a quartz, of a calcite cement in a dolostone. Yeah, and Julia published the paper in 2010 regarding this Knox dolostone, if you want to check it out.
All right, we have a question or a request for a comment from an anonymous attendee. The analogy of fractures from surface to subsurface can be very misleading due to huge tectonic differences between surface and subsurface that the rock has gone through, and the unconfined and confining local conditions between outcrop and subsurface. So you have any comments on making that leap from the outcrop to the core?
Yeah, that's a great question. So let me go to this one. I think this probably can help me explain. So here I'm showing both outcrop and subsurface, two subsurface examples, one outcrop sample. So we see in the outcrop, we are seeing a break apart surface, fracture surface. But what we're really hunting for is the quartz cementation that we can see on this fracture surface. So once I've identified a minimal quartz lining on this fracture surface, there are like rinds of small quartz cement nucleation on this fracture surface. And that's when we know the cementation happens in the subsurface. And then the reason why we can see them is because the rock itself got buried deep enough into the subsurface, maybe fracturing happened along the way, and then cementation happens in the subsurface because we need a higher enough temperature and fluid flow to precipitate quartz, right? Quartz cementation. Then after that, the rock got brought up into surface and split open. And that's why we can, present day, we can see the quartz cementation on this fractured surface at the outcrop. I'm not specifically hunting for like later stage cementation, like for example, calcite cementation in these rocks, because there's probably no way I can date them, and I will not be able to know when those cement form at what temperature. It's more it's less of a evidence compared to the quartz cementation we see on the fracture surface. So if that answers your question, and in the subsurface, obviously, if we know where the cores are from, at what depths, and we measure the temperature within the bridges. So we know when the fluid situation, like the temperature and the composition of the fluid when the fracture was forming, or at least when the fluid flowed through the fracture when it was still active and open. So with that, I would say we are able to identify when the fractures are formed. There's room for maybe I'm overkilling on this. Did I answer your question? I can give you more explanation and about how we date those fractures.
I think if there's any follow-up, our anonymous attendee can post another question to follow up. So we'll move on to the next question from Steve Nurek.
Yeah.
What is the value of fracture porosity?
That's a great question. So I would say there are cases where we think the fractures contribute more to permeability than the porosity, because from my experience for subsurface data set, the fracture porosity are usually less than 1% of total porosity. So you can count it but it contribute more to permeability, I would say. And there are cases, for example, I can tell you, I heard about some really deeply buried carbonate and sandstones, tight sandstones in Tarim Basin in northwest China. So there they have reservoirs at around like 8 kilometers, 9 kilometers depth. In that case, the rock matrix itself is super tight, but the zone, the area, the study area or their reservoir is heavily faulted and fractured, and their main reservoir body they're targeting are the areas along the fault. So the hypothesis is partly supported by some observations and production. So their main reservoir porosity is associated with the faults and the deformation zone of the fault. So in those cases, they value like a lot of the fracture porosity when they calculated like approximately how much production they can generate from those very deep and really tight reservoirs. But in my case, I would say in this Nugget sandstone, because it can be produced conventionally, and the fracture here are just added to the permeability and porosity. And Steve, you're right, fracture porosity in the Nugget case might not be as important. Yeah. And we have a question from Sun. Thanks for the great, yeah, thank you. Yes, yeah, we have example of applying NCC 1D to fault zone. My colleague, my fellow PhD student at FRAC, Rodrigo Corrier, I think he's in the audience as well. So he's trying to apply a NCC 1D to carbonate fault zones in an outcrop data set, southern France. I believe he gave a presentation maybe 1 or 2 months back at the PSGD. I can maybe Rodrigo can. Yeah, we can get back to you regarding his presentation and what he did with the fault zone study using NCC1D.
Yeah, that's available on our YouTube channel.
Yeah, sounds great. And fracture connection points are more favorable center for cement precipitation. Yeah, do we have data set to either support, discard, or control? That's a great question. So the fracture pattern, if you see, well, it really varies. Sometimes we just have a set of very maybe thin, long, parallel, individual, not well connected fractures. And sometimes we have a bunch of, small fractures that's also isolated, not well connected. And sometimes we have more like a chessboard pattern of fractures that's better connected. There are all sorts of patterns. And in terms of fracture connection points, I would say when two fractures start to grow towards each other and they see each other and eventually they link to each other, those connection points are usually smaller aperture compared to, for example, the middle part of the fracture. I think I'm showing you examples right here. Yeah, for example, this is what we would say for how in fracture aperture and cement texture varies from the center wider part of the fracture all the way to the tip of the fracture, right? If we're seeing another fracture maybe somewhere, oh, sorry, am I sharing my screen? Yeah, somewhere here, if there's another fracture and got linked to this fracture, I would imagine the connection points to be sealed if it's narrow enough. And there's, of course, this discussion around do we have enough fluid flow, enough silica, enough time for the fracture to be fully sealed at the connection points? That's a whole another discussion, but yeah. Yeah, if that answers your question. In other Nugget anticlines. Yeah, thank you, Orlando. Yeah. We have Steve's question. In other Nugget anticlines, the forelimb fractures are mainly shear fractures. Do you differentiate? Yeah, it's a great question. Yeah, if I would love to differentiate shear from tensile fractures, and I would love to, if I have access to the core, I would love to further QC those FMI picks. Those are QC'd and those are Terzaki corrected spacing values I used for the study. But yeah, I just don't have the data to differentiate shear and tensile fractures. And yeah, but that's a great point. Yeah, and in cases, I would expect shear and tensile fractures to have different pattern just because they're different types and mechanisms of forming. But that remains to be investigated further, I think. Jose, thank you. Microscope, petrographic samples. To modify the subsurface of fracture created through propellant action. It's very important for this type of reservoir stimulation to keep the fracture somehow open after the pressure pulse. I see. I see. So are you talking about the roughness of the fracture surface? Okay. I'm not 100% sure what you mean by propellant action. Do you mean
is that surface erosion of the fracture?
Surface erosion of the fracture by propellants?
I'm just
Is
guessing.
that?
I'm not understanding it either. Perhaps Jose could
Or can we
elaborate.
commute, like,
Maybe we can
unmute him? Maybe.
we can have, there is a question in the comments. So maybe if Jose can clarify what he means in his question, I can ask a question from Gary Prost. Oh, well, he just posted in the Q&A. So Gary asks, does this workflow allow you to predict fracture density, orientation, and clustering in the subsurface based on lithology, depth, and structural position?
That's a great question, and my really humble answer to that question would be, I'm showing a case study where I utilize the method to characterize the fracture pattern in a reservoir scale, structurally simple oil field anticline. In terms of predicting fracture density, orientation, and clustering, I would say if I have more data sets available, and if I'm allowed to, if I can compare, different lithologies, like, or like, yeah, that'll give me a more confidence in terms of how much predictive power this method have. But yeah, feel free to try the method out, try the workflow out for your data set, and maybe we can see if we find something similar, or you find some different results and you would have different interpretations. We can have a discussion around that. Yeah, but what I'm presenting here is a case study. Okay.
So Jose did post a little clarification. So it's a stimulation technique with high pressure gas or propellant.
Yeah, I defer this question to the engineers probably.
But Alfred Lacazette did have a response to this.
Right.
You'll let me read that. Alfred's response is propellant fractures are mode 1. Mode 1 fractures never perfectly reclose because of surface damage. Even when single crystals are split along a cleavage plane in a hard vacuum, the fracture cannot reclose completely. So I think that there is some permeability that will be retained,
right,
greater than the original matrix alone.
Yeah, we say once the fracture open, it's open. It can never go back to the original state.
Can't rebuild it. Can't stitch it back together unless you fill it with cement.
Right. Okay. Do we have more questions in the chat, or? I
don't see any other questions in the chat.
Yeah. Oh, and thank you, ST, for offering some other reference for the first question. Yeah.
And just for the audience, we'll post those references, links to those references, as well as Rodrigo's presentation in the description for this video.
Sounds great. Oh, and Alfred has one more, image log yourself. Yeah, I have, those are ancient, like old image logs. What I have are paper copies of the image logs. I don't have electronic copies. I QC'd some myself, and what I did was I decided, if some fracture picks are really absurd, or should I ditch a set of the picked fractures? After that QC, that's all I did. And yeah, some morphological characteristics, yeah, definitely, yes. But I would say for the nugget formation, in the image log, I do not see a whole lot of faults in most wells. The displacement show up on the image log just weren't enough to make the judgment. Yeah, but thank you. Yeah, that makes sense.